So homomorphism. Same and shape. But it's different than iso meaning same. So I don't know Greek very well, but I think it means more like same-ish. In this case, what we're talking about with homomorphism means that it will preserve the group operation. So the group operation from the one group to the other group is preserved. So then, yeah. So if we look at an example, might be looking at G equals the general linear group of 2 by 2 matrices with the real numbers. And we can define a function from G to the real numbers without 0, which sends a matrix A, B, C, D to its determinant, AD minus BC. In fact, I shouldn't even name it phi, I should just name it determinant. So we talk about that function in linear algebra. It's a super important function in linear algebra. And it's super important because it's a homomorphism, which we don't talk about in linear algebra, but we can talk about here. Okay? So the fact that the general linear group is matrices that are you're doing multiplication. And so this determinant function, it's the only function, in fact, that can do this. It's the only function that'll do this in a surjective way of preserving multiplication, which is why it's so important in linear algebra. And we introduced in linear algebra with how to use it, not necessarily like more about it. So in this class, we can look at it and say, what is this sort of thing? It is a homomorphism. So it's a homomorphism. And it's surjective. But of course, it's not injective. Surjective, also onto, but not injective. Which is also called one-to-one. Okay. Okay, the circle group. So we can send the real numbers with addition to the circle group, the fancy T, and this function is called CIS, I believe. So this is another function we've been dealing with already, but it turns out this function is a homomorphism. And it basically takes a real number, theta, and sends it to cis theta, which is basically the same as cosine of theta plus I sine of theta. And one of your homework problems was to show that this cis preserves like addition, which is basically that was proving that this function is a homomorphism. Okay. Let's see. All right, let's look at this properties of a homomorphism. Okay. So Proposition 11.4 says if you got the identity of if you got a homomorphism, in this case phi from G1 to G2, then it's going to send the identity to the identity, and it's going to send inverses to inverses. It's going to send subgroups to subgroups, and the inverse image of a subgroup is also a subgroup. So the subgroups to subgroups thing works both ways. And if you have a normal subgroup in the target, then whatever you sent to that normal subgroup is a normal subgroup in the source. So sometimes you can call these domain and range or domain and codomain, but oftentimes is it okay if I call them target and source? Or would you prefer domain and codomain? I'll say both. Okay. So target, source, domain, codomain. Notice you can't say range because the range is like what the function ends up hitting, not necessarily the set it's aiming at. Okay. Now, the proof, let's see, I want to make sure I don't prove anything that might be on the homework. 1, 2, 3, and 4, it's all there. All right. So the proof of 1 is quite cute. So let E be the identity of G1. And so where should we go from here? What do we need to show?
Identity of G2.
Uh-huh. Okay. Well, we can start with the fact that, let's see, one problem here is that we don't know if this is a surjective function. If it was surjective, then we could just pick something from G1 and do like inside and outside calculation. It's oh yeah, all right. That's better. Okay. We'll say E1 be the identity of G1 and E2 be the identity of G2. Okay. So we want to show, basically I'm going to write over here, I want to show that phi of E1 equals E2. This is the sort of equation I'm going for. Okay. So this is, side scratch work. So then, what are some things? So what are some things I could do here? I could say like create, that's like phi of E1 times E1. And that's like E2 times E2. And then this is homomorphism. So it's phi of E1 times phi of E1. No, that's not doing anything for me. I thought this was a cute and easy proof, but I've forgotten. Yes, okay. So I want this. So if I imagine like E2 times phi of E1. that's equal to just phi of E1, because E2 is the identity. That's equal to phi of E1 times E1. And that's a homomorphism. This is where we use the homomorphism property. Phi of E1 times phi of E1. And then by right cancellation, E2 equals phi of E1. So it's not just a cute proof, it's a tricky proof. It's a little bit of both, cute and tricky. All right, so how do we write that up? Then, basically just like I did over there, E2 times phi of E1 equals phi of E1 equals phi of E1 times E1 equals phi of E1 times phi of E1. And by right cancellation, E2 equals phi of E1. Thus, phi sends E1, E2. All right, that was proof of one. Okay, proof of two is also also fun. Let's see if we can figure it out. All right, so we're assuming assuming H1 is a subset of G or subgroup of G1. So make sure it's a sharp. And we want to show that H2 is a subgroup of phi of H1 is a subgroup of G2. Okay, so there's two ways when you want to show something is a subgroup, there's two ways to do it, right? You can use from our subgroup section, there's that proposition that says to prove a subgroup, you just have to show contains the identity, contains the inverse, and closed under multiplication. You can do it in like 3 parts. Or there's that other proposition that says show that A times B inverse is always in the group, right? And so those work in different ways. When you have when you know how to compute inverses, then the second one is better. If inverse computation is kind of like iffy, the first one's better. So here, I am assuming I've got group stuff. So I've got inverses to work with. I can just go for it. So I'll let X and Y elements of phi of H1. Okay. Now, what does that mean about those elements? What can I say about X and Y? Write that better. What does it mean about X and Y if they're in phi of H1?
Well, they're also in G of one.
They're in G2,
Oh, G2.
right?
Yeah.
Because they're in the target,
Mhm.
okay? Or the codomain. So what do we know about G1? How do they relate to G1? How do they relate to the domain, the source? you remember, this is going back to our first class, and we went through kind of like the intro to proofs review. So if I pick two elements that are part of like a function of a set, then what is the only thing I can say about them? It starts with there exists. Okay, I'm gonna write there exists and I can wait you guys out. All right. There exists what? Or even then there exists. Yes. Yep. There exists, I'll call them A and B from H1. Such that B, gotta zoom in and try to write that a little bit here. B of A equals X and B of B equals Y. Oh boy. I can't. I was going to try to do it with the fancy proposition, and I'm seeing a problem, a roadblock there. I think I would be assuming what I want to prove. So wait. No, I'm getting ahead of myself. Guys. I'm started proving 3. This is what I get for having a meeting right before class. Okay. Lost the circle. Okay. That's 3 now. Okay, 2. For 2, we're showing that inverses. So let G be an element of G1. Okay. This proof is going to be really similar to a proof from like when we first introduced groups. Do you remember, how do you show, so if you're trying to show this equation right here, what is another equation you can use to show this one?
I feel like you should use like the identity or something.
Yes. Yep.
Like or you have like an element times some other element that gives you the identity.
Yeah. So to show like that this is equal to that is take this times what's inside the brackets, see if you get the identity. So to say then phi of G inverse times phi of G, well, that's going to equal, it's a homomorphic. So it's phi of G inverse times G. Well, that's equal to phi of E 2. And I forgot to introduce E again. The identity of G. Or I've already introduced it. Sorry, I'm all over the place today. Just call it E1. Then that's equal to E2 by the last part. Thus, phi of G inverse equals phi of G inverse. If I multiply them together, I get the identity. So phi of G is the inverse of phi of G inverse. Okay, now I am ready to prove 3. And I have basically everything I need to do it the fast way. So I've got the subgroup H1 of G1. Pick 2 elements of phi of H1. Then there exists A and B in H1 such that phi of A equals X and phi of B equals Y. Then X, Y inverse, well, that's equal to phi of A, phi of B inverse. Well, that's equal to phi of A, phi of B inverse. The inverse can move inside. We just proved that in part 2. Well, that's equal to phi of A, B inverse. And then where is A and B inverse? Well, since AB inverse is an element of H1, because H1 is a subgroup, XY inverse is an element of phi of H1, by definition of what phi of H1 is. And that completes the proof. I showed it was a subgroup. By proposition, I can't remember the name. Phi of H1 is a subgroup. Of G2. Okay. Let's find the number of that proposition. Otherwise, it's going to bug me. This is in the subgroup section. It's like the last proposition. 331. Oh yeah, and it's non-empty, of course. Okay. So then proposition 331 is a subgroup of G2. All right. Questions there? We're the zoo animals today.
Yeah.
All right.
Just write stuff all over all the boards.
Oh yeah. Yeah. And then just be talking to her like, you are so smart. Yeah. Oh, love it. All right. Then if H2 is a subgroup of G2, then the inverse of it is a subgroup of G1. And the normality holds. All right, this is where, okay, so let H2 be a subgroup of G2. Okay. Let A and B. So I want to show that, what am I trying to show? I'm trying to show that phi inverse of H2 is a subgroup. So let A and B be elements of phi inverse of H2. So well, actually, I want to say something else first. Then or since E2 is an element of H2, remembering like E2 is the identity of the second group. And phi of E1 equals E2. We know that phi of H2 is not empty. Because E1 is an element of phi inverse of H2. Okay, we know that the homomorphisms always send identities to identities. We know that subgroups contain identities. Therefore, if I look at like, if this was only with sets, you might wonder, what if this is an empty set? So if you're just dealing like with sets and functions, it could be possible to have, when you're talking about this, like the inverse of a set being the empty set, like nothing is sent to that. But the identity is in H2, and the identity of the first group is sent to the identity of the second group. So E1 must be in there. Now, let A and B be elements of phi inverse of H2. I'm allowed to do that because it's non-empty. Okay, then what does it mean for them to be in there? Then there exists. Well, do I need to do this yet? Not sure. Yeah, it might work better. X and Y in H2 such that B of A equals X and B of B equals Y. Then AB inverse equals I don't know if I can just do it that quickly, can I? Because I can't do anything from there. You can't just do inverse function because you don't know if it exists. I could do phi of AB inverse, but I want to show it's a group. Yeah, I have to do this the slow way. Okay, well, I've already shown that H2 contains the identity. So I just need to show inverses and I need to show closed under multiplication. So then phi of, maybe we can try it. Let's see if we do it this way and see what happens. If I do phi of AB inverse. Well, that's equal to phi of A times phi of B inverse, because it's a homomorphism, which is equal to phi of A, phi of B to the inverse, because of part 2, which is equal to X times Y inverse, which is an element of H2. Thus, AB inverse is an element of phi inverse of H2. That's the definition of phi inverse of H2, is the elements from the domain that are sent to it. AB inverse is sent to H2, so it's in there. That shows that this is thus, my handwriting is getting worse and worse as I go here. Thus, phi inverse of H2 is a subgroup by proposition. What was that again? 331? Yeah, 331. Okay, the moral of the story, what are some things we could learn from this? Well, it's about knowing what you need to prove, basically. So when I need to prove that phi inverse is a subgroup, then I'm picking A and B in phi inverse of H2 and showing that AB inverse is in phi inverse of H2. But I can't just like start off with A times B inverse. I don't have enough information to know what to do with that. But I can look at phi of AB inverse and I get something that's in H2, which shows me that it's in phi inverse of H2. Okay? Now there's one last thing we need to show, that this subgroup is in fact normal. Okay? What's your favorite definition of normal subgroup? There's kind of a couple equivalent ones, right?
The left and the right cosets are equal.
Yeah, that's my favorite way to say it, but it's not my favorite way to prove with it. My favorite way to prove with it is like the show that like G inverse is contained in H. That's my favorite one to prove with. Okay, so let G be an element of G2. And I've already got, I've already got A and B in there. Well, I need to show it's normal in G1. So G1, sorry. Then G times A times G inverse. Ooh, yeah, and I gotta take phi of that whole thing. Because I don't know how to compute anything without taking phi of it. Going to equal. It's okay if I do a couple steps at once. Okay. Phi of G times phi of A times phi of G inverse. And since H2 is normal, and then I can actually use the, oh, did I ever show you guys the shorthand for normal subgroups? No, I don't think the textbook uses it. It's nifty sometimes. So you just, when you're writing, it's not very good for typing up a proof, but for right now, you take your less than or equal to sign and make it a triangle. That's the standard way of talking about normal subgroups. Since H2 is a normal subgroup of G2, this is an element of H2. Maybe it's okay if I re-say this in a shorter way. I'll just say element of H2 since H2 is a normal subgroup of G2. Okay. So if phi of something is in H2, then G inverse is an element of phi inverse of H2. And then by whatever theorem that was that you guys proved all the equivalent things for normality, so thus by proposition, can't remember the number, phi inverse of H2 is a normal subgroup of G1. Okay, let's find that proposition now. Those in the Normal subgroups. Theorem 10.3. Theorem 10.3. It's a normal subgroup. Okay. Questions about any of that? Mm. So. Oh. So that was a proposition. Then we got a couple theorems. Oh yeah, no, the last theorem of this section is that kernels so when you have phi from G to H, then everything that's sent to the identity of H. So let kernel of phi be defined as kernel of phi equals G in the domain such that phi of G equals EH, where EH is the identity of H. Okay. So before I go any further, let's go back to the examples from the beginning of class and compute the kernels. So, I was writing with very big handwriting up here. So in this example right here, what is the kernel of this homomorphism? Which matrices are getting sent to the identity?
I can't, I'm having trouble remembering what a kernel is.
Right. It's all the stuff that are sent to the identity.
Okay.
Mhm. All the elements sent to the identity. So, what matrices are sent to the identity? What is the kernel of this homomorphism?
Would just be where, the AD minus BC is one.
Yep. And do you remember, we had this, I don't know if any of you guys remember, this is okay if you don't remember. Do you remember that we had a special name for the matrices where AD minus BC equals 1? It was a special name. It was very special. It's the special linear group, SL2. That's the 2x2 matrices. Such that determinant or AD minus BC equals 1. So in this case, SL2 is equal to the kernel of the determinant homomorphism. Okay. What about this function that sends the sys function that sends real numbers to the unit circle? What's the kernel? Just name a few elements of the kernel. What are some elements of the real numbers that get sent to the identity of the unit circle, which is 1? What's that? Getting there, closer. So it's got to be a number. Zero, that's one of them. Not pi over 2. 2 pi, perhaps. Yep. Negative 2 pi, 4 pi, negative 4 pi. In fact, basically 2 pi times any integer. All right. So the kernel is always going to be a subgroup of the domain. It's all the things that are, and when the function is an isomorphism, the kernel is boring. It's the trivial subgroup. Because if the function's 1-to-1, then the only thing sent to the identity is the identity. Okay? So when functions are not 1-to-1, then they have interesting kernels. Okay? All right. So there's the kernel. And then we have a theorem. This it's like 11.5. Can't remember. Theorem 11.5. Says that basically, like, if phi from G to H is a homomorphism, I've heard some people pronounce it homomorphism, and I don't know if that's easier for you guys to call them homomorphisms or homomorphisms. I don't think it matters to me. Anyway, but so if that's a homomorphism, then the kernel of phi is a normal subgroup of G. All right, our proof, wait, let me just check. Is this there's no proof in the book. That means it might be a homework question. But think about the proposition right before it does all the work for you. fact, part 4 of the proposition above it does all the work for you. So that's all I'm going to say about that. Okay. How about some more examples? All right, they did that one. They did that one. How about if I had a function from the integers to the integers mod 5? And it basically sends sending like any a in the integers to like a in Z5. What would be the kernel of this function? Five is one of the elements of the kernel. What other elements would be in the kernel? Yeah, yep. So then the kernel C is like all multiples of 5. So if you ever were to go to graduate school, it would be really important where they talk about short exact sequences. And so, or this is also important if you ever go into like, you're interested in topological data analysis. Short exact sequences are important there too. But basically, you can create a bunch of functions where this is the function phi I just defined. This is inclusion, so you do iota. The Greek iota is I without the dot. That's iota makes an appearance in the Bible, like not to change one iota, it's the smallest Greek letter. And then this is you don't even need to name this one because there's only one way to send a trivial. Zero is like the trivial group. 0 with addition, just 0, and then 0 with addition. And so if you do it like this, then each of these functions, if you compose 2 of them, there's just nothing there. So 5z goes to the kernel of the next one. So that's what makes it a short exact sequence. And short exact sequences are important because it's like you're building up Z, you're showing how to build up Z with multiples of 5 and integers mod 5. Every integer is like a multiple of 5 plus an integer mod 5. In fact, that's the Euclidean algorithm. This is like a fancy way of saying the Euclidean algorithm is good. Is saying like you can write any integer as a multiple of 5 plus a remainder. Okay. All right. That's off topic. I'll get back on topic. All right. Yeah, that's about covers it. All right. Let's look at the homework. Well, not there. Where are we today? So 11 4, 8, and 9. Out of here. So 4. So number 4 will be a lot like the example we just did. 8. If G is a Abelian group, and you send the function is just like sending everything to their nth power. That's a homomorphism. So that should be a very short proof. 9. Then that is Abelian. Yes. So for 9, you might want to look a little bit at how we proved part 3, basically, of the proposition we just did in class. All right. Looks simple. You guys get free to get to work. I'll start putting in your quiz grades. And I'll end this guy.